Hi, this is Gustav Nelson doing video 3C for Calculus 1, and we have a cone with a point going downward that's leaking water at a rate of 35 centimeters cubed per second. The base radius of the tank is 1 meter, and the height of the tank is 2.5 meters. Now we want to know that when the depth, which is essentially just the height of the cone, is 1.25 meters, at what rate is the depth changing, which is the height, and at what rate is the radius changing? So the key to solving this is understanding that because we are in a cone, a right circular cone like this, that as the volume shrinks, the height of the cone of water and the radius of the cone of water remain constant to each other. So we know that at the beginning, the radius is 1 meter, or in this case, I'm just going to switch it all right now to centimeters. So the radius is 100 centimeters, and the height is 250 centimeters. We do these proportions. We see that the height is 2.5 r. And we're going to start with using the radius to solve the rest of the equation. So when we know that the height is 125 centimeters, we put that into the equation, and we see that the radius is 50 centimeters. Okay, so now we're going to work with the volume equation, and we're going to use the volume equation, isolating it for just the radius, finding the related rates, because we know that the constant rate of the volume change, we can then solve for the rate of change in radius. So the volume of a cone is 1/3 pi r squared times h. And here our h is 2.5 r, and that's really important that this is not in centimeters. This is just a constant rate. So we take the so we have 1/3 pi r squared times 2.5 r, which is the same as 1/3 pi r to the third times 2.5. We take the derivative of both sides, and we know the derivative of the volume in this case is 35 centimeters cubed per second, equals 1/3 pi times 3r squared times 2.5 times the derivative of r. And we get this because when we are finding the derivative of this r cubed, we first have to we do basically the inside derivative and then the derivative of the whole thing, like we learned before. So it's going to be 3r squared times the derivative of that inner r. So there's 3r squared times the derivative of that r. These 1/3 and that 3 cancel out. We reorganize this equation to solve for the derivative of r. We see that 35 centimeters cubed per second times pi times r squared times 2.5. And now this is very key. Here when I actually plug in the numbers, I see here I have centimeters squared down here. I have centimeters cubed up here. Those cancel out and leave us with centimeters per second. So that's how you know you have the right answer. I did this before, and I got it wrong. And I realized I got it wrong because I looked, and my units at the end of it were centimeters cubed. And I knew it couldn't be that because I was solving for the height. It had to have been centimeters per second. So plug all the numbers in. You get 0.00178 centimeters per second, which is the rate of change of the radius at the moment that the height is 1.25 meters. We can again use this related rate, or this related fixed ratio of height to radius. So we have 2.5 radius equals h. You get the derivative of both sides. We see that the 2.5 times the derivative of r will equal the derivative of h. Well, we just solved for the derivative of the r. So you plug that number in, and you get the derivative of the height, which at this point in time is 0.00446 centimeters per second. And yeah, that's the whole problem. This was the hardest one for me. It took me a long time to figure this out, mostly because I didn't switch to centimeters at the very beginning, and it just constantly messed me up. But yeah, after you solve it one or a few times, you get the hang of it.